Hello, my name is Jayanta Mandi and I'm going to present our paper Data Driven VRP, a neural network model to learn hidden preferences for VRP. This work is in joint collaboration with Rocsildes Canoy, Victor and my supervisor Tias. We are the members of VUB Data Analytics Laboratory. So in this work we focus on a real life problem faced by a small logistic company. They have a fleet of vehicles and in each day a set of customers they have to deliver goods. So it's a vehicle routing problem and they have a VRP software. Now we find out that the drivers are not satisfied with the solution of the VRP solver because the driver consider other factors such as availability of parking space, their lunch and rest place, and many other things. The drivers have implicit preferences or implicit knowledge about these things, and it's not easy to formalize them and to put it into a VRP formulation is next to impossible. So the planners manually modify the theoretical optimal route to come up with a solution which is acceptable to the driver. Our goal in this paper is to capture the preferences of the drivers and propose routes which would respect their preferences. Now in this way we want to eliminate or at least reduce the number of manual changes made by the planners, and we also want it to be adaptive so that if the preferences change over time we should be able to integrate that in our framework. So in this work we model the implicit preferences as transition probabilities between the nodes of the VRP, and we use a neural network model to estimate these transition probabilities. We start from our previous work where the probability is computed by enumerating path solution. In this work we improve this measure of probability by feeding it to a neural network model along with some other contextual and temporal features as input of the neural network. Also in practice we encounter that the company has a very small training data set, so we have to experiment with different architecture and different features so that we come up with a model with as few parameters as possible, which will help us to minimize overfitting. We also study two types of loss function to train this model: the cross entropy loss, which doesn't consider the VRP problem while training. On the other hand, the decision focus learning loss considers the VRP problem while training. So this is our starting point, the CP paper in 2019, where as the explicit specification of the preference is not possible, we define the preferences in terms of transition probabilities. So here the idea is that if a path is very frequent, then transition probability from the source node of that path to the destination node of that path will be high, and this will be a preferred path. So maximum likelihood routing is the one which maximizes the probability of the entire route, considering the route formation as a first order Markov model. And the formulation of the maximum likelihood routing is presented here. So it's easy to use it in a VRP problem. We just change the cost in terms of minus log Pij. Now computing the probability is a key part of this approach. In that work we compute it by enumerating the number of instances. We move from the source stop I to a destination stop j and then divide by the row sum. Now here we consider other features, temporal and contextual, such as day of week and distance between stops, and we hope to improve the transition probabilities. And we will also use the Markov probabilities as an input, and we want the output probability, the final output probability, to be a function of these input probabilities as well as function of the feature variables. And that's why we pass them to a neural network model, because we know neural network is considered as universal function approximator. Now, while choosing the right architecture for this model, we have to be very careful. We have to keep in mind that the company has very small amount of data, and this is because for a small company like this, each routing is realized in one day. So for a year of time, we have maximum 300 data points, excluding all the holidays and other stuff. So the point is, you have to be very careful in choosing the architecture and choosing the feature variables, so that in this case we avoid the overfitting. When we train with a small amount of data, overfitting is a serious concern. So what could be right architecture? Now here we present an example with only two features, the distance and the Markov probabilities between the stops. Now, as mentioned, the distance and the Markov probabilities are input of this network, and they are for each edge or each arc of the network. So we have 2 n square input, and the output again will be for each edge, so n square output. Now if we build a fully connected network, there will be huge number of parameters, and we will not be able to train such a huge model with limited amount of data. So we want to design a network with some structure, and that's why we only pass data of one stop to the model. Basically, both the distance and probabilities here are one row of one matrix, which we show in the last slide, and we use defined model for each source stop, and we pass only the data corresponding to one source stop to one model. Now once we have the input features, we do some feature engineering. Look, the output of the linear model is a normalized score, so ideally the input would also be unnormalized, and that's why we do log transform of the probabilities and log softmax of the distance. Note here that to avoid a fully connected network, the linear layer performs the linear combination of each destination stop separately. Basically what I mean is that the output wi1, this output, is determined by pi1 and di1 and not by pin or din. Now the output, these weights are unnormalized, so we have to do a softmax of these to come up with the final probabilities. So we have these following features. We have the day of week, the set of stops for each day, the distance between the stops which remain fixed for the entire period, and the number of available vehicles, and the past solution, and the transition probability is computed by Markov counting approach. So the past information is carried in two ways: the past solution directly, or also the transition Markov counting probabilities, which you also consider as an input. Now here we show the model with all the features. Now, like the probabilities, we have to do some transformation of the other features too, and that's why the linear block does linear combination of the past solution. Basically it assigns defined weight to defined days, and we learn these weight from the data. Similarly, the day of week and the set of stops are embedding are categorical variable, So we pass it to embedding layer to convert them into numerical features. So the idea is to learn the weights of the embedding layer as well as the weights of the linear loopback from the data, and that's why we train the whole model end to end. Now the structure of the linear layer and the softmax is same as the previous slide. Now to train the model we need a loss function. Now the model parameters should be updated by computing this loss and finding the derivative of this or the gradient of this loss function. The descent focus loss, so we have two different philosophy of loss. The descent focus loss aims to minimize the error after computing the VRP. On the other hand, the cross entropy loss minimizes the error before solving the VRP. I'm going to explain this in the next slides. The descent focus loss minimizes the error after VRP. So once we have the estimated probability, we have to find out the maximum likelihood routing using the predicted probabilities, and then we have to find the loss, which measures how the predicted route differs from the actual solution. So here is an example. We can see that these 6 edges are present in the actual solution but not in the predicted solution. So the loss metric here has 6. So this is the loss is 6 here. Now training with this loss comes with several challenges. First, to compute this loss we have to solve the VRP using the prediction, and that too for each instance repeatedly in every epoch, and clearly this creates a huge bottleneck while training. And also there's another severe problem, which is that once we compute the loss we have to find a derivative of the loss, and as the loss computation involves a VRP optimization problem, that means we have to differentiate the VRP problem again to find a find a derivative. Now for a combinatorial problem this derivative doesn't exist, because slight change in the input probability either doesn't change the routing or it changes the routing abruptly, so that either the gradient is 0 or the gradient doesn't exist. And this problem, means that as the gradient doesn't exist, this problem has been studied by various people, and what they do is to approximate the gradient by subgradient. In this work we follow the methodology of differentiation of black box combinatorial solver paper. They propose to compute the subgradient by perturbing the input probabilities and then taking the difference as an approximation of piecewise linear gradient function of that output space, and this way we find a subgradient. So in this case for each instance we are solving one extra VRP. The extra one is the one with the perturbed probabilities. So the bottleneck increase actually twofolds in this approach. To note in detail about this approach you can look at the paper. Another remark is that in their formulation the feasible region remains same for all instances, but we violate that assumption because in our case they have different set of stops, so the feasible region is not same. Now on the other hand, the cross entropy loss minimizes the error before solving the VRP, and it's a straightforward machine learning loss. So we pose it as a multi-class classification problem where we have to identify the correct destination stop for one source stop. Now compared to this descent focused learning loss, it's computationally efficient and the gradient exists and it's numerically stable, and so it's has advantage, and we can do the training for each source stop independent of another. Now these are the feature variables. Now as I mentioned that we want to avoid overfitting, we want to remove the redundant features, and that's why we block out one feature at a time. First we put the linear combination of the past solution. We've stopped it. In the next experiment we stop the stop information, then the weekday, then we stop the Markov probabilities, and next the distance feature. We also experiment with removing all the features but only with the input Markov probability feature. But again, the difference is that we still do a training to minimize the cross entropy loss instead of the raw probability we get from the Markov counting. Now for evaluation we have two criteria: root difference and arc difference. Root difference is how many number of minimal changes you have to make to convert the predicted routing to match the actual routing. So it's very similar to the edit distance. And the arc difference is, on the other hand, the number of edges traversed in the actual solution but not in the predicted solution. So this is actually similar. This is actually the measure of decision focused learning loss. So now we come to the experimental evaluation section. We can see when we use only the Markov probabilities, we have very low cross entropy loss in the training test dataset, as well as the low AD and RD. But when we use some other features, sometimes the cross entropy loss as well as the AD and RD increases. So this suggests there is overfitting. And when we remove the linear combination of the past solution, we find we attain the lowest cross entropy loss as well as lowest AD and RD. So basically it means that we should remove the linear combination of the past solution, because all information about the past solution is already contained in the Markov probability, so we don't need those features. That's how we attain the lowest AD and RD. So we choose this model and we compare with the Markov counting approach, and we show that again we have lower AD and RD than the Markov counting approach, and obviously low amount of cross entropy loss. And this is expected because we train the neural network to minimize the cross entropy loss, and it shows that in this way we are able to minimize both AD and RD. On the other hand, the distance based VRP, you can see it produce the lowest distance traverse, but this is not preferred. That's why the AD and RD is very high for this solution. When we experiment with the decision focused learning loss, we find out that the performance is not good on the test data. So we check on the training data set and we find out the AD is actually going down, but that doesn't reflect on the test data set. So this means that this is a case of overfitting, and our conclusion is that with such limited amount of data set, we can't train with decision focused learning loss, and also as we violate the one assumption. So basically the decision focused learning loss doesn't work because of these two factors. Now to conclude, we present a neural network model which captures the preferences in a CVRP setting. To train the neural network model, we study two kinds of loss function: the multi-class cross entropy loss and decision focused learning loss. Also, as we have the challenge of small data, we experiment with different architecture and different feature variable to choose the model with as few parameters as possible. And we find out that the cross entropy loss is computationally efficient, as well as its results in a better performance. And using the contextual and temporal feature, we are able to generate better measure of the transition probabilities, and with these better transition probabilities we show that we outperform the previous Markov counting approach, both in terms of arc difference and root difference. So this concludes our presentation. Thank you.